Hello friends, welcome to my channel Pharma-info with Shubhashish. Today the topic which we are going to deal with is SAR, that is structure-activity relationship of sympathomimetics, right? Sympathomimetics, it can also be called as adrenergic agonist or adrenergic drugs, right? Okay. We all know that sympathetic system, okay, it is out of proper functioning of this particular system, our heart rate, the rhythm, the blood pressure, the stimulation, at the same time relaxation of smooth muscle, all are being controlled, right? And we all know that the function which is served by sympathetic system, they are basically involves in expenditure of energy. Say for example, now I am delivering something in front of you, right? That means I have to liberate maximum amount of energy. I am a bit excited and all, because, and as a result of this excitation, definitely the moment you just measure my blood pressure, you can find a bit rise in my blood pressure, and that is nothing but that is because of the influence of the sympathetic system, right? So sympathetic system comprised of, because we all know that what exactly, I am not going in the pharmacological aspect of sympathetic system, right? But we all know that in order to proceed further, at least we should say a few things about the sympathetic system. We all know that it belongs to the main it belongs to autonomic nervous system, right? So under autonomic nervous system, sympathetic system is found to be one of the branch, which is often called as adrenergic system. Why? Because the sympathetic system, the nerves which are involved in sympathetic system, and we all know about neurohumoral transmission, right? It is the transmission of impulses across the nerves out of releasing a chemical, right? So here chemical, nerve means they should release a chemical, right? And the chemical is nothing but the neurotransmitter, which is responsible for, it is carrying the message along with it and deliver the message at a particular location, right? So that means, that is why it is called as neurohumoral transmission. Humor means chemical, right? And as it is involved in the nervous system and all that is why humor, right? Okay. So the thing is that under sympathetic system we have sympathetic receptors, and as there is a receptor, they should have their primary ligand. So here, as the primary ligand is involved in nervous system, so that is why it is called as neurotransmitter, right? So here basically under sympathetic system, the receptor, the target is found to be adrenergic receptor, right? Okay, if we just try to figure out their types or classes and all, we all know that they are split into two different branches, right? Alpha and beta. We have some sub branches as well. For beta we have 1, 2, 3. For alpha we have 1 to 2. Right? So these many splittings are there in the receptors and all, right? And their primary ligand or the primary neurotransmitter of this particular system, adrenergic system, is found to be adrenaline. So the neurotransmitter here is found to be adrenaline or noradrenaline and noradrenaline, right? Sometimes dopamine is also called as another neurotransmitter, okay, coming from this particular class, right? Okay. Now let me raise one question, right? That why dopamine is involved here? Because if we just try to figure out the making of noradrenaline, okay, it is originated from dopamine, right? So we can say that dopamine is found to be the precursor, the immediate precursor for the production of noradrenaline. I'll come to the structure and all. Now let me tell you one thing. Somebody has requested that in my previous videos that why not you come with some nomenclature of drugs and all, okay, and the tricks which are involved in remembering, in framing the nomenclatures without just mugging it up, right? Okay, we'll also discuss that one, because in the SAR study we'll bring few drugs and all, and we'll just deal with the nomenclature and the way we can just frame at least the structure partially, right? That I'm going to tell you today also. Right. So now let me just go to the mainstream, right? So just now we came to know that the adrenergic system comprised of two essential things. One is found to be the target. The target here is found to be the adrenergic receptor, and it is corresponding neurotransmitter or the ligand is found to be noradrenaline as well as adrenaline, right? Okay. Now, as I said, dopamine is also involved here, and dopamine is found to be the immediate precursor, right? So if we just try to knock dopamine, right, it says about dopa, right? Okay, dopa. So dopa, if we just knock dopa, we can get the information about the tyrosine, right? And if we just knock tyrosine, we can get the information of phenylalanine, right? So this is how it is biosynthesized. So phenylalanine, then tyrosine, then dopa, then dopamine, then noradrenaline, and finally adrenaline, right? And we are concerned about this, right? So this is found to be the biosynthetic pathway of what? Biosynthetic pathway of noradrenaline as well as adrenaline, right? Now if we just try to figure it out, okay, chemically, okay, how it looks, this is found to be the flowchart, right? From phenylalanine to tyrosine. And let me tell you one thing. It is not, see, all the things are not kept. All the intermediates involved in the production of noradrenaline as well as adrenaline, they are not being synthesized in a single compartment. There are different locations. Suppose from phenylalanine to tyrosine, right? You won't find it in the, adrenergic, cytoplasm, right? Or sometimes you can call it as exoplasm as well. So you won't find this in the adrenergic, this particular transformation within the adrenergic cytoplasm, right? This you cannot find, this particular thing you won't find in liver and all, right? So different locations are there where different intermediates are produced and just sent and it is being transferred to that, but to the next location, so that finally we can get noradrenaline as well as adrenaline. And once they are being formed, they are being stored within the storage vesicles, which are placed presynaptically, right? Chalo. So now phenylalanine, this is particular sequence, right? I'll come to the structural profile now, right? We'll just do a retro analysis, right? So first let us bring the structure of noradrenaline, okay? So how it looks actually. So this is something like this. So this is your noradrenaline, right? Okay. So this is noradrenaline. And how this will get converted to adrenaline? Simply you need to methylate this one. This has become what? This has become adrenaline. Now it is also having some other designation, right? Apart from calling it as a neurotransmitter, it can also be called as a hormone. That you know, right? Okay. So chalo, this is your adrenaline. If we just rub it off, demethylate it, this has become noradrenaline, right? If we just remove the beta hydroxy, this will become no longer it is in the form of noradrenaline, rather it has been converted to dopamine, right? Okay, dopamine. Now, if we just further carboxylate the alpha carbon, this has become dopa, right? So this is basically dihydroxy phenylalanine, right? So this is phenylalanine and we have put 2-hydroxyl here, okay? I'll come to it, the different, the nomenclature or different vocabs which are used for this particular structure and all. So this is dopa, right? If we just further go, remove this one, right? This hydroxyl, that means meta hydroxyl, right? This has become what? This has become tyrosine. This has become tyrosine. Okay, this has become tyrosine. And if we just try to remove this hydroxyl, now no longer it is in the form of tyrosine. It has become, the same tyrosine has become what? Phenylalanine, right? Okay. So chalo, so this is found to be the sequence, right? So it is, the starting material is found to be phenylalanine, which can produce what? Which is having an ability to get biotransformed subsequently and to produce noradrenaline as well as adrenaline. This is the making, okay? This is the making of noradrenaline, and which is, in a regular fashion, okay? It is observed in your system, in the living system, right? Chalo. Now, so what we observed in the structure of noradrenaline, that is It is holding a phenyl, and to that phenyl few hydroxyl groups are there, okay, and the phenyl is having a hydrocarbon side chain, right, at the terminal, and we have a terminally placed amino group, and to that hydrocarbon chain we have a hydroxyl, right. Okay, so let us just generalize the name, right. So the generalized representation of noradrenaline or adrenergic neurotransmitter is found to be what? Is found to be beta aryl ethyl amine, right? You can also call it as beta aryl alkyl amine. It is preferentially to be ethyl, right? So this is found to be the general name for this. General name for what? Adrenergic neurotransmitter. Because as we have seen in our earlier videos also, in the process of making a drug, first we should look after the receptor. We have to scale up the active site. We have to generate some knowledge about the active site composition and all. And we have to focus on the primary ligand, right, which is quite often been thrown within the active site, so that there is a formidable interaction. And once we are aware of the interaction and all, and from that we can develop some idea that what kind of substitution, because out of interaction you are acquainted with the functional groups which are there, which are involved in the process of interaction from both ends, from the receptor end and from the ligand end, right? Okay, so once you are aware of the fact that yes, these are the functional groups which are there in the primary ligand, on the basis of that only, you are just trying to substitute the functional group to generate what? Foreign entity, which we can call it as, we usually call it as a drug, right? Okay, check. So now let us see. So this is found to be the beta aryl ethyl amine, right? Okay, so this is found to be the general name. So now we'll see the SAR of what? SAR of sympathomimetics or directly acting sympathomimetics. So for the SAR purpose, we have to bring what? First we have to sketch, we have to develop a template structure, right? So the template structure is what? Beta aryl alkyl amine, right? Okay, chalo. So let us deal with the template structure first. So the template will be the primary ligand, okay, which is there in the adrenergic receptor, right? Okay. Okay. So this is found to be the template structure. This is found to be the template structure of what? This is found to be the template structure of noradrenaline or adrenergic drugs, right? Okay. Now let us just do one thing for our convenience, or for the convenience of presentation. We have to split the entire framework into three different fragments, right? Or three different portions, right? What are those? So this is one of the portion, that is aryl, where it is placed with respect to this terminal amine. This is the alpha position and this is found to be the beta position, right? So it is located at beta position. That is why beta aryl. So we have aryl. This is found to be the site 1. Site 1. Next we'll move to this alkyl chain. Alkyl chain, which we can call it as site 2. And finally we have the terminal amine. This is found to be the site 3. Okay. Now we'll just bring them one after another, right? Okay. Let us deal with the site 1 first. Okay. So now site 1. What we've observed here, a phenyl is essential, right? So what are the points that should be included in the site 1? Site 1, first and foremost, the phenyl is preferential. Phenyl is preferable. A phenyl ring is preferable, right? Okay. Chalo, phenyl ring is preferable. To that phenyl, two hydroxyl groups should be placed ortho to each other. That means the catechol is preferable. For the proper affinity to the receptor to grow, the catechol ring is found to be one of the essential features to be kept. So that means apart from this phenyl, I can just straightway call it as catechol. For optimum affinity. And when there is an optimum affinity, what we can expect? When there is an optimum affinity, we can expect optimum biological response, optimum intrinsic activity, right? Chalo. So that means catechol. Why it is catechol? Because catechol is a stuff in which phenyl to a phenyl, two hydroxyl groups are attached which are ortho to each other. We are not looking to this particular part. Straightway we just consider this as a separate entity, and the separate entity is holding what? Two hydroxyl which are ortho to each other, right? Chalo. Now let us see what will happen if I just start modifying either of the hydroxyl. So what they are telling that removal of this meta hydroxyl, rather what they are telling, this can be said in otherwise in a different way. What they are telling that substituting or replacement of this meta hydroxy with a similar kind of functional groups. What does it mean? Replacement of this meta hydroxyl with a similar kind of functional groups. What does it mean? That means the way hydroxyl is interacting with its corresponding receptor active site or corresponding amino acid. That means we need to search, we need to replace the hydroxyl with another fragment, another substituent which should mimic the interaction profile of this hydroxyl. That means what does it mean actually? Suppose ki, let me just see, okay, let me just bring methyl. So what kind of interaction that is growing here? It is expected that a hydroxyl group is there. So that means probably out of hydrogen bonding interaction, okay, it is just contributing. It is out of hydrogen bonding interaction with, suppose ki one serine is there, which is providing another hydroxyl, right? And to this hydroxyl, what happened? Hydrogen bonding is taking place, right? So it is one of the interaction, okay? It is one out of so many, it is one of the interaction, and that is essential, right? So now the thing is that instead of hydroxyl, if I just introduce methyl, what will happen? No longer hydrogen bond can be made here, can be found here. So that means I start losing one point of contact, right? So that means, and it will be reflected in my biological response, right? So that means methyl should not be an ideal substitute for this hydroxyl. That means I need to search another fragment which should mimic the chemical as well as the physical profile of this hydroxyl. This can be something like CH2OH. The moment I am just replacing the hydroxyl with a CH2OH, what will happen? Just observe what will happen. So this is OH. So definitely as serine is waiting here, so we can expect hydrogen bonding here. So that is why they are telling, you have to keep it in your mind that yes, serine is waiting here. That means hydrogen bonding is found to be one of the interaction that is likely to be happened here. So that means you have to keep it in your mind that we have to search for an entity which is as similar as that of hydroxyl. That means the entity should have a similar physical as well as chemical property as that of hydroxyl group. So that is why you are supposed to substitute this with a hydroxymethyl, and this you can find in the adnergic drug called salbutamol. So it is in the salbutamol you can find CH2OH at this particular location, right? So this is one of the things. Now, what will happen if I just replace the catecholic hydroxyl or the meta hydroxyl with another kind of substituent? What they observe that out of this substitution, the drug is growing affinity towards beta receptor. So it is the beta 2, preferentially beta 2 affinity increases the moment we are replacing meta hydroxy of this catechol with a similar kind of functional group. Okay, so that means if you want to increase the beta 2 selectivity, and what for we are after beta 2 selectivity, we all know that salbutamol is a drug which can be given to the patient who is suffering from asthma, right? So that means there is a bronchial congestion, at the same time bronchoconstriction, and it is out of what? It is out of smooth muscle, bronchial smooth muscle contraction, right? So all we want is most of this salbutamol, what exactly they are doing? They are just trying to relax, expand the bronchial airways so that the patient will feel much comfort, right, in inhaling as well as exhaling, right? So that means it is the beta 2 receptor which is located in the bronchial smooth muscle. Stimulation of beta 2 receptor often results in the expansion, relaxation of bronchial smooth muscle, and which we are after. So that is why in the process of increasing the beta 2 selectivity, one in other way, you are just expanding the bronchial airways by relaxing the bronchial smooth muscle. Why? Because beta 2 is located within the bronchial smooth muscle, right? Chalo. So that means this is clear. That means this is clear. Okay. So that means hydroxyl we can replace it with what? Replace it with near equal functional groups. Okay. That means the functional groups which should mimic the physical as well as chemical property of this hydroxyl group. That means which are quite capable of forming hydrogen bond with the serine hydroxyl, right? Okay, chalo. And we have seen as a part of this particular replacement process, we have seen that beta 2 selectivity increases, right? Okay. Now, okay, let us just deal with the site 1, right? Because the board was a bit clumsy, right? It's very difficult to understand, right? What exactly I mean. So the first thing that is site 1, what kind of modification? At least one modification we found where at meta-hydroxyl, right? You have to replace it with a near equal functional group so that it can also form hydrogen bond, so that we can avail the point of attachment or point of interaction, right? That particular point of interaction. And we have seen that as a part of this modification or as a result of this modification, we can get beta 2 selective agonist, okay, which can be given to the patient who is suffering from asthma, right? Chalo. And the drug is found to be salbutamol, salmeterol and all these things. Chalo. Now, let us see that in site 1, whether it can afford a few other modification as well. So this is found to be the site 1, right? Okay. And we have with us 2-hydroxyl, right? Okay. So what the second thing that we can say, that is positional alteration of either of the hydroxyl group. Positional alteration. That means if we want to make it a different analog of catechol, what should be the analog of catechol? We can say if we just replace or just push the hydroxyl from here to here, this will become what? They are no longer in a ortho to each other. They are in meta to each other. So that means we have got another kind of analog of what? Catechol. This has become resorcinol. So what they observe that, okay, keeping everything same, if we just alter the position of the catecholic hydroxyl from para to the meta, what happened? They found that beta affinity increases. Beta affinity increases and preferentially beta 2. Preferentially beta 2. That means again we can avail the service provided by the beta 2 stimulation. That means bronchial expansion, okay, can be exploited in dealing with asthma, right? Chalo. And we have a drug called terbutaline, or we can say metaproteinol. Metaproteinol, terbutaline, okay, these are the drugs in which you can find that no longer catechol ring is there, right? The catechol has been shifted to or changed to resorcinol, right? So this is found to be the resorcinol. So another modification I told, right? Now let us again deal with this catechol, right? Okay, let us see that what is the other thing. Okay, let us see. Okay, what they observe. The next point is this I should right. Okay. Chalo. The another point in site 1 is what they observe. What they found that if we just replace the para-hydroxyl, removal of para-hydroxyl will lead to what? Will lead to the development of affinity towards alpha receptor, right? So alpha affinity increases. Alpha receptor affinity increases the moment I am replacing. I am replacing means I am just removing. Upon removal of the para-hydroxyl leads to development of affinity towards alpha receptor. That means alpha affinity increases on removal of para-hydroxy, right? So that means all we want is the para-hydroxyl should not be there. The moment you are just removing para-hydroxyl, what will happen? You can find the affinity towards alpha receptor. We have an example that is phenylephrine. Okay, in case of phenylephrine, you won't find it to be acting on beta receptor. Instead, it is predominant on alpha receptor. Predominant on alpha receptor, right? So this is about another, kind of ECS study, okay, which they carried out, right? Okay. Now, so this is all about your site 1. Okay. Now, I'm left with another. Okay. As I told that, okay, we have removed one hydroxyl. What will happen if I just remove both the hydroxyl? Yes, that is also possible. What to observe that on removal of both the hydroxyl, that means all we want is, earlier it was catechol, later we have just transformed into a phenol, and now we don't want phenol to be existing there. And that is why both the hydroxyl has been removed. We have just made it what? Simply a benzene or phenyl. The moment we have just made it benzene, keeping everything same, okay, what they observe that now this has become an agent which can act in an indirect way, but still adrenergic agonist. We have an example called ephedrine. Ephedrine is an example. We have another example called amphetamine. In case of amphetamine, okay, you can find both the drugs, they are acting on sympathetic system, and they are just stimulating the sympathetic system. That means they are found to be sympathomimetics or adrenergic agonists, right? But they are not directly approaching the receptor. Instead, they are called as indirectly acting sympathomimetic. Indirectly acting sympathomimetic. But let me give you one example, one information about this amphetamine. Amphetamine can appear in a pair of enantiomer, right? One enantiomer is acting on autonomic nervous system and the other enantiomer, so it is the R form of amphetamine that is acting on ANS, that means sympathetic system, whereas the S form is no longer having an affinity or growing an affinity towards autonomic nervous system, rather it is developing its affinity towards central nervous system. That is why amphetamine is a CNS acting drug, sometimes we can call it as. But both the forms are not found to be a CNS active. It is the S form that is found to be CNS acting, whereas the R form is found to be ANS acting, right? So we are done with the site 1 modification. What kind of modification? So in a nutshell, we can just summarize it. What are the things that we studied in site 1 modification? What are the modifications that are preferable or that are acceptable in site 1? What we observe? In a nutshell, let us just deal with that first. In a moment, we'll just, in a nutshell. So first, what we observe? Catechol essential. Catechol essential, right? Essential for both the affinity, that means alpha and beta. Then what we observe that meta-hydroxy of catechol replaced with similar functional groups resulting beta affinity to grow. Preferentially beta 2 receptor. We are after beta 2 receptor, right? Next thing what we observe that positional alteration of catechol. Positional alteration of catechol hydroxyl to resorcinolic hydroxyl. To resorcinol leads to what? Leads to again beta affinity and preferentially beta 2 selectivity. Then what we observe? Removal of what? Removal of para-hydroxyl. Results in the affinity grows towards alpha receptor, right? Then removal of both hydroxyl. That means catecholic hydroxyl leads to the development of indirectly acting sympathomimetics. Sympathomimetics. Okay, so with that we are done with what? Site 1 modification. Okay. So now site 2. So we are done with site 1. Next site 2. Site 2 means we have an aryl. To this aryl, aliphatic chain is attached, right? Aliphatic chain is attached. Okay. And to that aliphatic chain, at this location we have a hydroxyl, right? So what they are telling, or what they are suggesting rather, or they suggested that in order to retain or in order to develop the optimum activity or affinity, right, the hydrocarbon chain should be made up of 2 carbons. That means neither lengthening to 3 nor shortening to 1. It should be kept 2 for the optimum activity. Got my point? So that means in order to develop the optimum affinity, okay, the hydrocarbon chain, okay, which is attached to the aromatic ring should remain in the form of 2. That means a chain of 2 carbon should be kept immediate after this aromatic ring. So that means to the aromatic ring, the chain which should be there should compose of 2 carbon. Neither lengthening to 3 nor shortening to 1 is found to be acceptable. Got my point? Okay, that means we have a chain called alkyl. The alkyl is preferentially an ethyl. So it is the ethyl from which we can get the maximum affinity. We can expect the maximum output from this ethyl, right? Now let us find that hydroxyl has been kept here, right? Okay. In order to grow the optimum affinity, a hydroxyl group has to be placed at beta position. Why I am calling it as beta? Because immediate next to this carbon we have a nitrogen, right? So this is found to be the first one, nitrogen. To this is found to be the alpha, this is found to be the beta. So that means the one beta hydroxyl, that means at beta carbon we have to place a hydroxyl group. A hydroxyl group has to, a polar functional group has to be inserted at beta carbon, okay, of this beta aryl alkyl amine. Okay, it is the hydroxyl. The moment you have inserted one hydroxyl, what happened? Now the pro-chiral center, which was earlier found to be something like this, has become a chiral center, and as a result of this chirality, as the chirality develops, so that means as a result of this, it can appear in 2 forms. That means a pair of enantiomer. I am calling it as, I am just trying to say pair of enantiomer, right? It has been observed. Now when there is a generation of pair of enantiomer, that means we cannot expect that a similar extent of activity from both the isomers, right? So that means the activity definitely will differ. So what to observe, that most of the sympathomimetics of direct class, it is the R form that is found to be pharmacologically relevant, pharmacologically predominant, right? So it is the R form that is dominating the process of what? Biological response, right? So this is found to be more active than that of the S form for most of the sympathomimetics of direct class. Got my point? Chalo. So this is, so what we understood here, it is the side 2 should be made up of 2 carbons, right? To these 2 carbons at the beta carbon we have to insert one hydroxyl group in order to strengthen the activity, because we have another residue or amino acid here, right, with which the hydroxyl will form hydrogen bond. And why there is a difference in activity between these 2 isomers, this can be readily explained from here. Why? Because now assume that this is found to be the R form. In the R form, the hydroxyl group is found to be just below the plane. Just below the plane. That means it can readily access the hydroxyl or carbonyl, okay, from this end, which is coming from the receptor end, right? Okay, with which the hydroxyl has to form a hydrogen bond, right? Now what will happen? The moment it just change its orientation, because the moment we are dealing with S, definitely the hydroxyl group will change its orientation, spatial arrangement. Earlier it was in this location, now it has been shifted from here to here. Now it's very hard for this hydroxyl to access the hydroxyl of this amino acid, okay, which is found to be one of the composition of the receptor active site, right? So as it cannot avail this particular attachment, so that is why there is a deviation in the intensity of the activity. Got my point? Okay, chalo. So now with that I am done with the explanation, right? I am still I'm left with another point, right, in this section, right? Okay, now coming to this particular section, I have put here R, right? Okay, R. Sometimes it has been found that a smaller alkyl group at alpha carbon is preferable, right? The moment you are just putting a smaller alkyl group at alpha carbon, what will happen? Suddenly you have found an agent which has developed and which is showing more affinity towards alpha receptor, preferentially alpha 2 receptor. That means alpha 2 affinity increases when the alpha carbon is substituted with a smaller alkyl. So that means branching of this alpha carbon with a smaller alkyl as methyl leads to the production of an agent which is found to be alpha 2 selective. So that means alpha 2 adnergic selective or selective alpha 2 adnergic receptor agonist, selective alpha 2 adrenergic receptor agonist develops the moment you are going for branching. You are going for what? You are going for branching of this particular alpha carbon. So that means insertion of a smaller alkyl to this carbon, that is alpha carbon, okay, smaller alkyl is found to be methyl, leads to development of an agent which grows affinity towards alpha 2 receptor. And we all know that what will happen as a result of alpha 2 stimulation. Alpha 2 receptor being placed presynaptically, acting as an autoreceptor, and we all know that when there is an excess release of noradrenaline or adrenaline at synaptic cleft, it will be readily taken up by this autoreceptor. So that means as we are just stimulating the functioning profile of alpha 2 receptor and assuming that the subject is suffering from hypertension, that means there is an excess release of noradrenaline at synaptic cleft. So that means whatever excess things are there, under the influence of this alpha 2 stimulation, hyperstimulation, because we are stimulating it, alpha 2 selective, right, with an agent. Okay, we have an example called alpha methyl dopa. Alpha methyl dopa, right? In case of alpha methyl dopa, you can find a methyl group at this location, right? So it is the alpha methyl dopa that is found to be a selective alpha 2 agonist given to the patient who is suffering from hypertension. Why? Because alpha 2 being placed presynaptically have a control over the excess release. When there is an excess release at the synaptic cleft, it is being readily taken up so that it can nullify the mal effect, the ill effect, okay, of this noradrenaline, right? So that means alpha 2 receptor can be considered as an antihypertensive. Why? Because it can stop or it can nullify, neutralize the hypersecretion of noradrenaline or adrenaline at synaptic cleft. Got my point? Chalo. So we are done with this, and moreover, at least by introducing an alkyl group at this location may also lead to what? Lead to the development of resistance towards metabolizing enzyme. That means you can also have an effect, have a control over the metabolism, the degradation. That means you can extend the duration of action by inserting an alkyl group here, because you are just by putting an alkyl group at this location, you are just making this particular area resistant towards MAO, monoamino oxidase. Okay, so the moment it is developing resistance towards MAO, what will happen? Metabolism will get slowed down, and as the metabolism will get slowed down, so what will happen? The drug will stay in your system for a prolonged period of time. So that means you can just extend the duration of action. Got my point? So that means this agent, which is having a alpha methyl, okay, in addition to its alpha 2 selectivity, it can also grow resistance towards metabolizing enzyme, and as a result of it, we can extend the duration of action, right? Okay, I forgot to tell you one thing in site 1 under this metabolism and all, because as I have just brought the topic called metabolism. So in case of site 1, we talked about the modification and all, right? But we have not discussed that whether they are found to be metabolically resistant or not, right? Okay, there I told that okay, we can just alter the meta-hydroxyl group, right? Okay, the moment we are altering meta-hydroxyl, we are getting a product which is growing affinity towards beta 2 receptor, right? In addition to this, it is also developing resistance towards COMT. So what is COMT? COMT is catechol orthomethyl transferase. Catechol orthomethyl transferase. So assume that this is found to be the catechol. So under the influence of this COMT, what will happen? This will become methoxy. The moment this will become methoxy, what will happen? No longer it is being accepted by the receptor, right? So that means it is the COMT that is trying to degrade catecholamines or noradrenaline, okay? And that is being prevented once you are just modifying this hydroxyl to a like this. Got my point? So that means in addition to this beta selectivity, it is also developing resistance towards COMT, okay? And so this is the effect of what? Meta substitution. In addition to this, the moment we have shifted the catecholic hydroxyl from ortho to meta, there also we can avail the same thing. That means these are the agents which can also grow resistance towards or develop resistance towards COMT. Why? Because no longer there is a catechol nucleus. The catechol has been changed to resorcinol, as in case of metaproteinol as well as tarbutaline, right? Okay. So this is about your metabolizing enzyme and all. So in a nutshell, what we studied in this site 2 modification, we have seen that the prerequisite is found to be the 2 carbon chain. neither lengthening nor shortening is found to be acceptable, right? We have seen, yes, the beta carbon can be substituted with a hydroxyl so that we can strengthen the affinity and all. And moreover, we have seen that sometimes the alpha carbon can also be branched with a smaller alkyl. The moment you are going for branching of this alpha carbon, what will happen as a result of it? There is an increased affinity grows towards the alpha 2 receptor, and which can be used as an antihypertensive. Okay, the justific and the logic behind that I told you, right? And moreover, the moment you are just putting an alkyl group here, you are just resisting, you are just developing a resistance towards MAO, so that metabolism will get slowed down. As a result of this, the duration of action of that particular drug will get enhanced, right? So with that we are done with site 2 modification, right?